taking classes, but it's not possible here. Number two, the board, chalk and talk is the best method so far I have experienced, so that we are missing, but still it's our challenge to provide you as much as possible through PowerPoint presentation and through verbal interaction. So it needs a lot of cooperation from your side, because I can't see you. So it is you have to take the initiative to be highly in the class by your full attention and mind. Okay, because learning spirit is very intrinsic spirit. Everyone does that. Okay, so let me go to the presentation mode, and I will be sharing the entire screen to present the PowerPoint file, and that would be on quantum. Okay, what do you see now on the screen? What do you see now on the screen? Is it a PowerPoint page?
Yes, sir.
Okay, what is written over there?
Welcome to a
Treasure house.
Welcome to a
Treasure house. So again, once again, we are welcome to a treasure house, a wonderland. Okay, Alice, you all now are Alice, and you all are now in a wonderland. We are entering the wonderland. So my role would be to open the wonderland, to show you something that you see something is there in the land, in the treasure house, and then to awaken you. Okay, if some of you are sleeping, then I will awaken, and then I will allow you to enter, and then you will play in your own way. Okay, so that is the motto, and this is the title: Exploring the Quantum World, a cartoonist's view, to be delivered by me, Priyotosh Datta. Well, the basic reference, my acknowledgement, is this book, Introducing Quantum Theory, a Graphic Guide. Okay, so this is my acknowledgement that I have taken all the cartoons from this book, but I have compiled in my own way, of course. A few references are there. Well, you need not, right now you did not go through all this by details, but these are the references, not textbooks. Okay, some other kind of books. For any subject, you know, if you want to grasp the subject particularly in depth, then you have to read some other books as well other than the textbooks. So these are such books which I have read, and that always helps. But I would not suggest every student to go through all these books, because they are not textbooks and we don't have that much of time to go through these books. But this red letter, 30 years that shook the world of physics, George Gamow. I think the Gamow spelling is wrong, probably double M would be there. This is a book I will suggest you that if you have some of the hobby of reading books, different types of books, then in your leisure time you should consult this book sometime, or you can suggest to your younger brothers and sisters to go through this book. This is the history of quantum physics, quantum, written by none other than one of the greatest scientists, George Gamow. Well, introducing quantum theory. So I will read out the quotes. Okay, so these two fellows are talking. So many people are there actually. You know, it's easier to explain quantum theory to an absolute beginner than to a classical physicist. And he is answering that you are kidding. What's the problem? These classical guys with the modern theory. So they are talking about a new theory, and they are saying that, okay, a believer, I mean, just start a beginner, he can understand it properly. But once you are an adamant classical scientist, then probably it's difficult for you to understand and grasp or believe the prerequisites and outcomes of quantum theory. Then one such example, you know, the whole classical science, classical mechanics or classical physics, it has two of the most cherished academic data in the history of thought. It has provided. One is, the Newtonian mechanics, and the other is Maxwell's electromagnetism, right? And this fellow, can you guess who is this picture? Of course, the quotation would make it very clear. My gravitation, Isaac Newton. My gravitation law has been used to predict measured movements of the planets with great accuracy. So that is the winning race started from, you can say, the modern science, Newton. And then comes, can you guess this man before, just from the picture? But if I read out the quotes, then probably it will be very clear. Okay, let me read it. I predicted the existence of invisible light waves in my electromagnetic wave theory of 1865. And Heinrich Hertz detected that signals in his Berlin laboratory. Now they are called radio waves. So can you predict, can you guess this person?
De Broglie.
No, sir. 1865, much earlier to
Maxwell.
Yeah, thank you.
Maxwell.
It's Maxwell. And Maxwell is talking about he is talking about his own theory, for two pairs of equations called electromagnetic wave equations he has given, and that explain the whole lot of behavior of light, of course the classical behavior of light. So almost nothing new was left after his theory about light. Apparently it seemed so until we got in the 20th century, but before that he was the boss, because his theory was experimentally proved, verified by this person, Hertz. These waves reflect and refract just like light. Maxwell was right. So this is the pair, okay, theory experiment pair, Maxwell Hertz. So that is another winning stroke of classical science. And then you are very much used to this thing, selfie. So as if I call it a great selfie, the classical physicist to commemorate the development of classical physics. So all they are from different part of time, but imaginary they have assembled together with a hi-fi mobile to have a selfie. And you see the names. It starts from Archimedes, Kepler, Newton, Galileo, Faraday, and Maxwell. And what they are saying, it is comparable to seeing us posing together for selfie to commemorate the development of classical physics. So it's a good selfie, a good picture. Is it? Isn't it? It's an interesting picture. A good selfie, better selfie than yours. How many of you are used to selfie? All of you?
Yes, sir.
Yes, sir. Good.
Yes, sir.
Okay. So we are talking about the victory of classical physics. So it's a long story, but to cut it short, what are the fundamental assumptions of classical physics? What they talk about the material world around you. So the first one, determinism. Nothing was uncertain, only a consequence of some earlier cause, right? So everything is determined, deterministic. Light are completely described by Maxwell's electromagnetic wave theory. This is their concept. Two physical models, the particle and the wave models, are mutually exclusive. That is, energy must be either one or the other. So they are explaining matter, the material world, in terms of particle, and at the same time they are talking about waves when they are coming in terms of light. So they are saying that okay, both the things, particles nature and wave natures are there, but they are mutually exclusive, either this or that, right? So that is their way of perception. They looked at the world in such a way, and it was impossible to measure to any degree of accuracy the properties of a system, like its temperature or speed. So it seems everything is deterministic, and if you have a good instrument, you can measure anything. Of course, it is measurable something. Then you can measure it very accurately, 100% accuracy. provided in principle, provided you can have a good device, sophisticated instrument, measuring instrument, that and the thing has to be measurable. Now if you ask the classical scientist, can you measure accurately the amount of love I have for him or her? No, love is not something that scientifically can be measured by some instrument, or the amount of fear, or the amount of, the existence of soul and the existence of God. So these are out of science periphery, right? They don't ask these silly questions, that they are not observable, they are not measurable. So that is beyond science. And classical physicists believed all these statements to be absolutely true. That is the danger. So it's a lesson for us that you cannot be probably absolutely true, whatever it is. So better to keep some uncertainty, some uncertainty, some messy. But they thought that what they know about the classical science world is absolutely true. But for all four above assumptions or statements would eventually prove to be in cloud of doubt, right? So unfortunately, gradually in the later part of the 19th century and particularly in the beginning of the 20th century, they were proved not to be wrong, but proved to be partially true and partially wrong. How? That we'll explain. And what were those two clouds? Now it says that, how was I to know that one of these clouds would disappear only with the advent of relativity and the other would lead to quantum theory? So that's why we are here in this class, quantum theory. So the two basic clouds over there, over the classical science, was removed. One of by these two clouds, one of them is removed by none other than quantum theory. Of course, the other one is relativity. So that's why we call the modern science components are relativity and quantum theory. Okay. Now how and who have done all those things? Who are that group of physicists who removed these two clouds? Who are those physicists? Not one or two or three, actually a group of physicists. Okay. Of course, some are more important than others, but all were important, and that is the group. You can't identify all of them right now, but one or two you can identify. Okay, you just have a few seconds. Try to at least trace or identify one of them. One is prominent figure. Try to guess.
Einstein, sir.
Einstein is there. Okay, good. That is visible. He is in the middle. In the middle, right? This is Einstein. Now, even if you cannot identify the figures, but you know a lot from your graduation courses, so can you predict a few more names, just arbitrarily?
Curie, Madame Curie, and Avogadro.
Avogadro is not a quantum scientist. I am talking about after you see the year 1927.
Niels Bohr.
Bohr is okay. Bohr is fine. Okay, Bohr is here. This is Bohr.
Max Planck.
Niels Bohr. Max Planck.
Sir Rutherford.
Max Planck is here. Right.
Sir Schrodinger.
Schrodinger. Right. Thomson. Okay.
Sir Rutherford.
Rutherford. Okay. Go ahead.
Dirac.
Dirac,
Sir
of course.
Curie,
Of
Madame
course.
Curie.
Madame
Sommerfeld.
Curie. Sommerfeld. Any other name?
Heisenberg.
Heisenberg. Very good. Heisenberg. So you know a lot about that. Itself reflects that you know a lot about that part of science, quantum science. This is the group. Okay, and you know there is hardly, if you compare this particular period of time, there are hardly any period in the history of science in which so much has been clarified by so few and in so short a time. So this is very unique of this development of this period. And out of many, I will call that 9.
Sir.
Yeah.
Sir, was that a picture of the Solvay conference?
Exactly, 1927 Solvay conference. Right. So I think it is written over there or not. Let me see. Brussels, Solvay, right? Brussels, Solvay, right? You are right.
Okay, sir.
So now, out of so many, but let me pick up some of the greatest of the great, 9 Nobel laureates. So I have listed 7 and mentioned 2 and. So you have to fill up this 2 and. You just have a glance. Niels Bohr, Schrödinger, Pauli, Heisenberg, Dirac, de Broglie, Max Born. So almost all the names you have mentioned in your response, and I have told that 9, but here you have got 7. So can you fill in the blank, this 2 and who are not in this?
I think it's Curie. Curie, Madam Curie.
No.
Schrodinger.
Schrodinger is already there. Arvind Schrodinger.
Okay.
Max Planck.
Repeat.
Max Planck, sir.
Yeah, one of the and is Max Planck, because you can say the birth of quantum. Okay, the birth of quantum is Max at the hand of Max Planck. He's the, you can say roughly, he's the partly the mother of quantum. Though by gender he is a father, but whenever we say, we call in this way that mother of something. Fathers are not given honor that much. So mother of quantum is one of the Max Planck, and another is Einstein, of course. Of course, Einstein is not in this list. So including Max Planck and Einstein and these 7, they are the 9 gems. Okay. Of course, a few more are there in quantum development. Now the question is, are they experimentalists or were they theoreticians or were they both? Or particularly the question is, what experiments compel them to ignore the tenets of the classical physics and propose ideas and nature that violated common sense? Right. So a quantum concepts to start with are so awkward, unbelievable, that it defies your common sense. You will say, okay, we will respond like, is it? No, it's not possible. But your experimental result says so, that no, it is like that. So quantum science in its deep level of understanding, it's full of such surprises, that goes against your common sense. But common sense is common, right? Common sense may not be always common. So you need some experimental help. And my question is, what are those landmark paradigm shift experiments that led some of the scientists to think in other way? Of course, though it was against their common sense. So now I will talk about 3 such experiments. Can you give some?
Sir?
Yeah.
Sir,
Yeah.
sir, Richard Feynman was also very instrumental in quantum mechanics, even though he was a physicist.
All of his system. Yeah, you are right. You are right, Feynman. But Feynman came into the picture long after this initial development. He came after 1930s, right? And as I mentioned the book, 30 years that shook the world of physics, right? George Gamow.
Yes, sir.
It explains the period of 1900 to 1930. So what I am referring as that period is this 30 years, and then Feynman, of course, was one of the important figure. Of course, you are right. So, are you getting an echo of my sound? No. If someone is on in mic, then only the echo is there. Otherwise, it's okay. Is it okay now? My voice is it okay?
Yes, sir.
Okay.
Yes, sir. It is okay.
Okay. So I am talking about a few experiments, right? Now I am leaving it to you. That can you predict, or you have already known actually all those experiments, but may not be that you have thought in that way. That what are 1, 2, 3, the 3 major experiments? Can you predict? Can you give some light? Any one of you? What are those 3 experiments that actually changed the perception of about the world and gradually switched over from classical to quantum world? That means,
Sir, আমি একটু বলবো?
yes.
Sir, is it Schrodinger's cat?
Schrodinger's cat.
Schrodinger's cat is
Okay, any other point?
স্যার বলছে আগে তো ভাবা হতো কিন্তু সব ট্রানজিশনই মানে পসিবল, তো তারপর লাইন স্পেক্ট্রা দেখা হলো, তো তাই জন্য মানে সব ট্রানজিশন তো পসিবল না, সেখান থেকে একটা কোয়ান্টামের ধারণা।
Okay, that we have got another point. Any other point? Any other student?
Sir, double slit experiment.
Double slit experiment. Okay, that's a good point. Any other point? You have missed the very first one, which is associated with the birth of quantum.
So photoelectric effect.
It is not really the
Sir,
birth.
Bohr's model.
Bohr's model in 1913.
I think Rutherford model.
Rutherford model about the atomic structure, but he didn't give anything quantum idea. Okay, photoelectric effect is one of the most starting important point experiment, of course. But I told you that that experiment associated with the very birth of quantum theory, quantum concepts, and this person is
diffraction, light diffraction করতে গিয়ে ওই যে মানে
no diffraction double slit experiment, that's okay, but that is diffraction can be explained by the wave theory of light itself. It doesn't need any quantum theory. I am giving you some hint that this fellow is responsible for that explanation, new explanation of that experimental results, which are not being able to be explained by classical science existing at that time. So let me read it out.
dual nature of light.
It came much later, 1920.
So the gold foil experiment.
No. Okay, now and at the second hint, I am reading.
So black body radiation.
Good. Black body radiation. This is Max Planck.
Max Planck.
Yeah. So now let me thank you. You have given all the three. What I wanted from you, you have given all the three. Thank you very much. The first one is, of course, the Planck's black body radiation. So what he says, you see, I started it all in 1900. Okay, that is the year of birth. By postulating that matter can absorb and emit electromagnetic radiation, that is light, whose size is proportional to the frequency of that radiation. And you know the Planck's hypothesis, everyone remembers from graduation courses, En equal to nh nu, isn't it? So that is all about. That amount of light absorbed or emitted is in a quantized fashion, not continuously. So that is the first time we got some peculiar, awkward, new idea, quantization. That something is in nature, something is happening in a quantized fashion, not in an arbitrary continuous fashion, but in quantized fashion. But it was given by Planck in explaining the black body radiation. Let me go ahead. Just a minute. Yeah. Okay. The next slide. Now you will see something interesting. I am reading it out one by one. This man, who is this man? Is very visible. This man is saying something here, and this man is
Einstein.
And can you guess this person? Is that face is popular to you, known to you?
Niels Bohr.
Good, Niels Bohr. So it's a dialogue between hypothetical dialogue between not hypothetical, it really happened so, Einstein and Bohr. Einstein is saying that I showed that light always exists as quanta, which is why matter absorbs and emits it as such. Too bad Planck never believed me. So that is very interesting to see historically. What he is saying, that light itself exists as quanta, and that's why matter absorbs and emits it as such. So the second part is already given by Planck, that black body absorbs and emits in quanta. But why so? Fundamentally, Planck didn't dare to go to answer that question, that why fundamentally black body is absorbing in such quantized fashion, right? He didn't dare, because the probable answer that came 5 years later from Einstein, the probable answer actually Planck didn't believe. So that means you have given birth to a baby and you are not believing that it is your baby. I mean, the baby at all is there, this kind of thing. So that is very interesting historically. That Planck, he himself didn't believe his theory because it went against his common sense. So he was divided into, mentally divided in two parts. One part is his prejudice, his so-called belief, the existing, the training, etc., which says that no, it's not possible. On the other end, the physics mind, the mathematical intuitive mind of Planck is saying that black body is behaving like that is absorbing and emitting in quantized fashion. That's why he didn't explore it further, that why this is fundamentally so. And then Einstein came forward. He is saying, you see, it's very easy. Black body is emitting or absorbing the light in quanta because light itself is quanta, right? So that is the thing Einstein is saying that Planck didn't believe. And now you see what is a conversation between Bohr and Einstein. Now Bohr is saying, I reviewed the probabilistic interpretation of quantum theory to the apparent satisfaction of mostly everyone except Einstein. So again there is a contradiction. Einstein and Planck, right? And now another pair, Planck and Bohr. Bohr is saying that the way it is leading to, it must be probabilistic, not deterministic. But Einstein again didn't believe the concept or perception of Bohr. So they are talking about some conception, theoretical ideas, right? They are not talking about any experiment, because as far as the experiment is concerned, the basic quantum mechanics which came later on, as far as the mechanics is concerned, they all agreed. There was no confusion, no debate. But as far as the interpretation of quantum theories, the explanation on what does it mean, that means the philosophy behind the theories, as far as the philosophy is concerned, they were splitted. They were in different groups. Planck, Einstein, Bohr, and then some other people joined, de Broglie, Heisenberg, Schrödinger, etc., etc. So that is very interesting historically, right? And I will come later to that point. So what are the experiments? As we have already mentioned, the first one is black body. Just a minute. The first one is black body, and the year is 1900, and the man behind is Planck. And after just 5 years, 1905, the experiment was photoelectric effect, that also you have mentioned. And the man behind is Einstein, 1905, after 5 years. And then one of you have mentioned the line spectra, that is the Bohr's theory of atom, bright line optical spectra. So before that, no one could dare to explain that why the hydrogen spectra should be there at all and in that line fashion, right? It should be continuous, because in nature nothing is quantized, everything is continuous, continuously changing, is starting from your age, time, the length of a tree, everything is changing in every microsecond or milliseconds or femtoseconds. That means it's continuously changing. But first time they're talking about, all these three people are talking about something quanta. Bohr is talking about the quantization of angular momentum, as you know from your class 11-12 course, that mvr equals to nh2 pi. That means he was talking about the quantization of something, and that something is in that case angular momentum. And then Einstein, earlier to Bohr, he was talking about the quanta, and that time it was the light itself, the energy of light is quantized, nh nu, because n is the number which is bound to be integer, not any arbitrary number. That's why the energy is quantized. nh nu proportional to frequency. So for a given frequency, nu is fixed, suppose, then the energy can be nh nu. So h is a constant, nu is fixed, suppose. So h nu is, you can take 1 unit. Then the amount of energy of light can be 1 unit, 2 unit, 3 unit, that is n is 1, 2, 3, n h nu, but nothing between 2 or 3 or 3 or 4 or 4 or 5. So you can't say that 3.5 light energy unit, 3.5 or 3.75 unit of energy. You cannot think of in quantum. It is always 5 units, 6 units, 7 units quantized. Okay, and at the beginning it was the quantization of the amount of radiation emitted or absorbed by black body. You see the difference. It looks that Einstein and Planck, they are talking about almost the same thing. No, they are talking very differently. Black body radiation gives you the idea that what is quantized over there? It is the amount of light radiated or emitted, absorbed. Okay, that amount is quantized. It's not talking about light directly. And Einstein is going one step further. He is saying that the light energy itself is quantized. And then Bohr is talking about that, okay, light is coming from a body. So if light is quantized, amount is quantized, then why not that the light from where it is coming, that itself is quantized? That means the structure of the system, that means atom, molecule, they are also quantized. That's why we got the hydrogen theorem of Bohr. So these are the 3 experimental results explained by new ideas, which consist of the old quantum theory. You say this is of course quantum, but we call it old quantum because till then we didn't get any suitable mathematical tool, the mechanics, to deal with all these newer concepts, and that came much later through the hand of Schrödinger. And then through Schrödinger we got the $1 million equation, Schrödinger equation, and that gives rise to the mechanics part of the quantum. So quantum theory is one thing and quantum mechanics is other thing, and when you are applying this theory and mechanics in chemistry, then we call it quantum chemistry, right? So don't confuse with these words: quantum theory, quantum mechanics, quantum chemistry. Well, these are the things that you know, that Planck, this is the black body as if, and the distribution of light intensity is like this at different temperatures, and fortunately it goes through a maximum and then it falls down. Otherwise, you know, ultraviolet catastrophe would be there. That is also very known to you. What is the attempt? The experimental results were known even before 1900, right? It was known, the black body radiation experimental results, but people, it's not that people have not tried. The classical physicists, they have tried but failed. For 2 such examples are Rayleigh Jeans and Wien. So this is the experimental curve, the lower one, right? So you see some of the dots are there on the right hand side. That means these dots were explained by the Wien displacement law, but only the part of the whole, right? Only right hand side. On the other end, these dots were explained by Rayleigh Jeans, the lower frequency part. So both of them could explain only part of the fact, but none of them could explain the whole of the fact, and that's why we needed another one, third person, and that is Max Planck. So Planck gave you the idea, some idea that I have mentioned, that quantization of amount of light energy, and ultraviolet catastrophe, because if Rayleigh is right, unfortunately Rayleigh is not right. If Rayleigh is right, then with frequency, the intensity radiated from a black body, that means a hot body, is going on and on and on, right? So you just think of your fireplace, right? In a cold winter, you are just enjoying the evening in front of a fireplace, and it's radiating light, but it's radiating light of what frequencies? So many frequencies, but the intensity of the frequencies, different frequencies coming out of that fireplace, is gradually increasing on and on and on with more and more higher frequency. Now, after a certain limit, you know, the frequencies are harmful, very harmful. Say for example, VGR, the violet is the light of maximum frequency out of the visible light. Now, after violet, what comes? Ultraviolet, right? And then X-ray, gamma ray, etc. And you know that X-ray is harmful, gamma ray is very harmful, and ultraviolet is also directly harmful for your body, for the living body. So if it so happens that more and more frequency light are coming in more and more amount just from a simple black body, that is fireplace or a hot iron ball, then it will be dangerous, right? it will burn you, it will harm you to the any extent. And that is the picture. The next picture is this. Okay, it says that he is enjoying, the Max Planck is enjoying the fireplace. Here the fireplace, it's Max Planck, and he's saying that I would have my eyeballs burned out. अगर ऐसा होता तो प्लैंक का तस्वीर ऐसे लगता है, right? Burned out. So this is the ultraviolet catastrophe concept, ultraviolet catastrophe. But in nature it doesn't happen, but Rayleigh and Jeans predicted in that way. So how Planck resolved the problem? As I mentioned that HF1, F is frequency, so HF1, HF2. So as if this is a pack of light energy and he is just chopping it out by different units, right? So I found that I had to choose energy units proportional to the oscillator's frequencies, namely E equal to HF, in order to obtain the correct form for the total energy. F is the frequency and H is a constant which would eventually decrease to 0. That part I explained, that is coming up and then falling down. So which religions failed to explain. Planck just introduced this simple but new concept that En is NH, if nu or F, whatever it is. Then it after a little bit of mathematical manipulation, he could be able to show that okay, no, don't worry, ultraviolet catastrophe is not the natural fact. Intensity will go initially half with increasing frequency, but then after a certain limit it will go down. So we are safe, we are not suffering from ultraviolet catastrophe. So that is the concept of Planck. And then comes, okay, I was so skeptical of the universality of Boltzmann's entropy law that I spent years trying to explain my results in a less revolutionary way. So that is the intuitive mind. Planck introduced the new concept, but he was not believing, as I have already mentioned, that he was not believing the underlying physics or underlying philosophy of that concept. He tried to explain in his own way, excluding this probabilistic or statistical behavior of this quantum world, that means Boltzmann's world, but he failed. So he is saying that nevertheless quantum theory had been born. So I tried my best in explaining it in my own classical way, but I failed, and so unfortunately quantum world is born, and born in my hand. Born in my hand. Okay, so a father is not believing his daughter or son. Well, concept of quantization. And then come, who is this person? 1905. The picture is quite visible. Who is this person?
Einstein.
Einstein.
এবার কারো ভুল হবে না. So what he is doing? What he is doing? He is walking on the street and engaged in writing something one after another, and he just throwing it out all the pages. So that means actually this picture represents that Einstein in this 1905 is writing so many papers, more than 1, 2, 3, 4, and just is throwing it out to the people that okay, you see, this is called science. So these were the light quantum paper, which concerns us now, a second seminal paper which proved the existence of atoms, and a third which introduced relativity, solving serious problems in electrodynamics and motion. So that is very, very interesting. You know, the if someone is there, so many bosses are there in every field, right? Starting from football, cricket, science, art, so many bosses, but hardly you can call all of them the big boss. So to me personally, there are so many bosses in science, also in quantum science, but the big boss was, of course, Albert Einstein. In a single year, 1905, in a single year, he published 5 papers in the same journal, and all those 5 papers deserved Nobel Prize. People say like that. But it is not possible that a single man will get 5 Nobel Prizes in a single year. It's not possible. So people are bound to give him a single Nobel for that year work. Actually, he got his Nobel much later, but the job was done in 1905. So he did 5 papers. One of them was on relativity in 1905, which is special relativity. In 1913, of course, he gave general relativity later on. One of the paper was on Brownian motion. One of the paper was on light quantum or photoelectric effect. And he got a Nobel Prize for one of these 5 papers. Can you predict, or can you guess rather, for which he got his Nobel Prize?
Photoelectric effect.
Photoelectric
Photoelectric effect.
Are you sure it is not relativity?
Yes, sir.
Yes, sir. Okay, thank you. Yes, it is photoelectric effect. And that, a simple concept was introduced again, and that is NH nu. So, you may ask a question here at this point, and that is very relevant and interesting question. Yes, sir, a few minutes back, you have shown that this is the formula, and remarkable revolutionary formula introduced by Planck in 1900 to explain the black body radiation quantum effect. And again in 1905, we are again saying that E equal to NH nu is the same formula explaining the photoelectric effect. So is it not ridiculous that the same formula got Nobel prizes twice, E equal to NH nu? So first of all, you express me that are you surprised with this fact that it is the same formula brought 2 Nobel Prizes just within a span of 5 years? Is it so that within a span of 5 years, so many things have changed? So the Nobel Committee have been changed, and the committee members are quite new, so they were not aware of that, the fact that NH nu has already been given the Nobel Prize. So they by mistake gave it again to Einstein. Is it like that? Or some fundamental something somewhere is there? But first of all, you explain that, not explain, you just express yourself that are you surprised to see this fact, to know this fact, and you are observing it first time. Someone is telling you for the first time that this kind of thing has happened in the history of science. Any one of you?
Yes, sir.
Yes, sir.
Yeah. So it is a bit surprising. Thank you. But actually, it is not that like that. Of course, the formula are looking the same, but the interpretations are different. When Planck introduced E equal to NH nu, the left hand side E was the energy amount emitted or absorbed. That's all, right? Emitted or absorbed light, but it's not talking directly, not anything about light itself. The amount is quantized. That's fine. But Einstein went a step further. He is saying, Planck, what you are saying is because what I am saying, that light energy itself is quantized. So E is NH nu in Einstein's formula. It is even more revolutionary that energy of light itself is quantized. And what was the concept before that, earlier to Einstein's concept of light? It was the Maxwell's concept that light is wave, and as usual, as it happens to any wave, the energy of light is proportional to the intensity of light. And intensity of light can be anything, not quantized, arbitrarily any value from 0 to infinity, continuously varying. So energy of light in classical light, it can be anything, because intensities can be anything and energy is proportional to some of intensity. So energy of light can be anything. That was the continuous energy concept of light. But now we are getting, as we call it more popularly, particle character of light. Particle character of light. And here it says that energy of light for a given frequency cannot be any energy, but 1 unit, 2 unit, 3 unit, dot, dot, dot. So a kind of quantization in energy itself of light is there. So I think the point is clear that how really the formula are different as far as their underlying interpretation is concerned. I think it's clear, right? To add one or two points more, when something is continuous, suppose you are in a shop and you are asking for some sorse tel, mustard oil. So what you say that okay, give me this much of oil, and that this much can be any value, right? You can ask for 100 gram, you can ask for 101, 101.5, whatever it is, right? So you can take any, that means the amount you can propose for can be continuously varying something, right? So how much? But when you ask for, suppose you have gone for cigarettes for your father, not for yourself. So you are buying some cigarettes. Then do you ask that give me how much or how many? What you ask for? How much cigarette or how many cigarette? You ask for how many.
How many?
Because you don't ask. You usually ask give me 5 cigarettes, 10 cigarettes, 9 cigarettes, 1 cigarette. So they are integer units, right? You never say Kaku give me 3.5 cigarettes. The Kaku will say what will do with the half one, and who will buy the other half. So it's not possible, you cannot buy cigarettes by that quantity, 3.5, पौने 4 cigarette दाओ, 7.5 cigarette दाओ. You never say, right? So as if light was initially it was how much, that is continuous something. Now suddenly it has become how many, like cigarettes, right? Like particles. So that's how the concept we call it particle behavior of light. One of the reasons is behind the calling it particle behavior or particle nature of light after Einstein. Okay, is it clear the point? You see, everyone knew this concept, but it was, I think it is not that transparent, that how really they differ, why we call particle, in what sense particle is there in light, right? So some of the concepts were not very clear, I think. Well, so a same equation earned Nobel twice. It is the innovation, quite a revolution in concept, not the mathematical sophistication. It is the conceptual something. Well, and then came the bright, the light spectra, the secrets of atom, the third experiment. So the photoelectric, Planck's black body, the one, first one, second one is photoelectric effect, the third one is the line spectra. So before Bohr came into the picture, this man, Balmer, and a few more actually, they could not explain, they could fit some empirical formula to explain the line spectra. But they didn't know about the physics, that why they are suggesting such formula. Balmer's and a few more are there in a series, Balmer series. A few other names are there, I have forgotten. Right. So as if they were playing with number and they were playing with some puzzle, a jigsaw puzzle, and they were in search of a suitable formula so that it explain the line spectra. They could give it, but they didn't give any explanation for that formula. Why the formula is so, they were completely in dark unless Bohr came into the picture. So Rydberg constant, and this is the formula they could suggest, that the frequency of the line spectral frequency is like this. R is some constant and this is the number, integer number of initial and final level. But why the formula is like that, how they have got it, they didn't know anything. And then come this man. I started at the Cavendish under J.J. Thomson, but did not get on with the great man, especially after he told me how disappointed he was in my pudding model of the atom. So these two fellows, this is the teacher J.J. Thomson, and Niels Bohr was working with at that time with Thomson, and it was around 1900 something. So Thomson was proposing a model of an atomic structure, And you know, everyone from class 9, 10 or probably or maybe 11, 12, the pudding model of structure. So like this. But Bohr has strong objection, and that's John Thomson is saying that he was disappointed to get this idea of atomic structure. So he was not happy, right? Bohr was not happy. Then this is the central premise of my scheme. Now Bohr is himself proposing a new scheme, the quantization of the electron orbits in the atom in units of Planck's constant. So Bohr was thinking that how the spectra is line spectra, not a continuous spectra. So something is quantized, because already in his mind quantization concept is there. It was already introduced by Planck and by Einstein in two different perspectives. So he was thinking of that, okay, in my problem, that is hydrogen problem, how I can probably introduce some quantization somewhere of something in my model. So he introduced, of course you know that he introduced what, but initially thought of that electrons are moving around the nucleus, but probably not in any arbitrary continuously varying distance from the nucleus. That means if you call it an orbit, the radius of orbit is not continuously varying, rather it is somehow, because of some reason, it must be quantized. So that's how he brought into the picture some quantization. And then but he was curious to know, but why should it should be so? So fundamentally you have to propose something, some quantization. It's not about the orbit length. It came much later. So as you know, so he was just thinking and on and on and on. He was dancing, but inside, he was dancing with ideas, but not around the edge. He was dancing like this. That means going into the depth of something, and it looks like a dancing lady, and these lines represents the rotational motion of this lady, dancing lady. Actually, these are the orbits of hydrogen atom, and he got his idea that what is basically and primarily quantized, that is the angular momentum of electron while is rotating around the nucleus. And angular momentum is I into omega, and that you can show very easily that actually that reduces to mvr, which is angular momentum, because I is mr square and omega is v by r. So mr square into v by r cancel out, so it gives you mvr. And his new idea is that this mvr or angular momentum L must be proportional to this h by 2 pi, and n is the constant, but this n is not any arbitrary number, but it has to be integer number. So that is the beauty of this single simple looking expression line, that n is not any arbitrary number, but n is integer. So somehow is forcing the electron to rotate in such a way that your angular momentum can have 1 unit, where 1 unit is h by 2 pi. So it can have 1 unit or 2 unit or 3 unit like cigarette. We cannot ask for the angular momentum of an electron of 3.5 unit or 4 unit, right? You cannot, because that is the theory tells about. So n is integer. So you see how basically a simple mathematical concept is controlling the whole perspective, n, and n is a number which has to be integer. In Planck it was nh nu, in photoelectric effect again it is nh nu, and in Bohr's theory again it is n h by 2 pi, where h and pi are constants, right? So that is how he thought, going into the depth. So if you want to dumps, you have to dumps in this way, going into the depth, not by surface study. So these are the things you know. As a result, finally Bohr could calculate the energy levels En, and En for E1, E2, E3, and then he could calculate the difference between the levels, delta E, N1 to N2, and that delta E is when divided by H, that gives you the frequency, and that frequency did exactly match the experimental frequency obtained from line spectra. So now we can say that yes, we have a strong theoretical foundation for why hydrogen spectra have to be line spectra, right? And the foundation is basically founded on the simple concept that angular momentum of electron is quantized, right? So that is the beauty, you know, that simple concept, but how profound the concept is. So what we got from Rydberg and others, Balmer, etc., without any theoretical foundation, now we have got the basic theoretical foundation of that formula that has already been solved, given by some many people, but without knowing the physics. But now we know the physics, that what's really happening in inner world of the atom, that is quantization. So that is the Bohr's theory. And not only that, we had some more experimental result, ionization potential. That means how much energy is required to eject an electron from a stable hydrogen atom to infinity. How much energy? That we call ionization potential. And it was experimentally known that it is 13.6 electron volt. And now people were eagerly asking Bohr that okay, if you have provided a theory for hydrogen atom, then your theory should be able to explain mathematically and quantitatively that it should be 13.6 electron volt. And Bohr told okay, let us try. And then what he did in his formula, he initially put 1 and in final he put infinity, because he wants to eject the electron from the first orbit to the infinity, and the result gives exactly 13.6 electron volt. Beautiful. Would you call it beautiful? Any one of you? Can you hear me? Can you hear me?
Yes, sir.
Yeah. So doesn't look it very beautiful, something that is simple and profound concept, how it explains the experimental result, isn't it? The whole quantum is actually so surprising, so against the common sense, so beautiful, and on the other hand so simple, but so profound philosophically, right? So and we then later on we got so many things explained. You know, in 1890s, Mendeleev did a lot of labor, put a lot of labor, sweat and blood over constructing the periodic table. So much of experiment, so much of data he collected, analyzed and put in order to get finally the periodic table, right? He is famous for that, Mendeleev periodic table. But after getting the quantum theory, the atomic structure, now just on a pen and paper in an AC room, on the chair, armchair, you can explain the whole periodic table, that why the periodic table looks like that. So is it not that something amazing that you have some ideas that explains the whole periodic table? What he says, Mendeleev, I had realized that the chemical properties of the elements were repeated if arrayed in a table of rows and columns according to increasing atomic number, right? That he did. But Bohr explained the periodic table just by a theory. So I suggested that the chemical and physical properties of an element depend on how the electrons are arranged around the nucleus, and I pictured the electrons as grouped together in layers or cells, that is quantized orbit, right? And thus Bohr could explain the whole periodic table by his simple atomic theory of hydrogen, right? So that is awesome, that is amazing. Well, would you like to take a break at this point, or should I go ahead? I have a few minutes more, but I have taken a lengthy one. So if you just want to take a break for, so let me go ahead. Thank you. Now, after these three giant, one more is coming. Who? Here comes a connoisseur of music who was curious to know, is quantization typically a micro world phenomenon? So he was a young man. He was asking himself that this peculiar world, quantum world, that means the micro world, atom, electron, molecules, and everywhere it is quantized. Quantization is there. But is it only in the micro world? Is it not available in the macro world, in our visible world anywhere? But fortunately, he was a music lover, right? Can you guess who the person is I'm going to talk about? Just a wild guess you can give. Music, connoisseur of music. Of course, I'm not going to talk about Zakir Hussain or Hariprasad Chaurasia or Nikhil Banerjee or Ravi Shankar.
Sir, Feynman.
No, not Feynman.
Sir, is it Schrödinger?
Not even Schrödinger.
Dirac. Paul Dirac.
Well, you will get it after a few seconds. He was asking that does anything of visible or audible world, which is not the typical micro quantum world, so does anything of visible or audible world manifest quantization? That was the question. And music inspired him to find the answer. So that is something new also, I think, to you, that how in the whole picture of quantum development, how music contributed, right? Because music has a very old history. Now, what particular part of music actually inspired this person? What he wanted, he chose to see an atom as a musical instrument, and something is quantized, and it emits certain basic tone and a sequence of overtones, and he knew that length of the string. So think of setar, sarod, behala, violin, and any other string instrument, and that much of physics, music physics or physics of music, he knew that length of the string, it must be half integral n by 2 of standing sound waves. So lambda by 2, its integral multiple, that means n lambda by 2, and that should be the length of the string. So this equation was known to him from music, and that's why lambda is 2L by n. This he knew, and pictorially it would be like this. So the first one is lambda by 2 into 1. 1 is the smallest integer, you know, positive integer. So 1 into lambda by 2. So this is the length of the instrument, suppose, and it can accommodate 1 into lambda by 2, that means half of the wave. So a half wave is there, standing wave, and then it should be the n equal to 2. So the length should be 2 into lambda by 2, that is lambda, that means a complete wavelength. So you think of a complete wave inside the box, that means the instrument. So this is lambda by 2, this is 2 lambda by 2, and if you go on, so 1 lambda by 2, 2 lambda by 2, dot dot dot, n lambda by 2. So L is n lambda by 2, that he is getting from music. So what does it tell? He suddenly surprised and discovered that, well, in the audible world, in the world of music, something is quantized, and that is wavelength, because lambda is 2L by n or L is n lambda by 2. So wavelength is quantized, right? So something interesting. L is n lambda by 2 and lambda is 2L by n. So the wavelength is integer. Somehow n is there, and that n is not any number but integer number, right? And that's how he could think that, okay, if I somehow can introduce the wavelength concept in my quantum world aspect, wavelength concept, then because wavelength is quantized in the musical instrument, so also it would give you the same quantization effect in quantum world also. But for that purpose, what he has to introduce? A concept of wave and wavelength. But how you can do? Then he thought of that, why not? That if I think that an electron, okay, Bohr is talking about electron, if I think that electron is behaving like wave, then I can introduce the wavelength, and then I can introduce the wavelength is quantized, and that would explain the whole lot. So that's how he thought an atom as a musical instrument and introduced the wave concept or wavelength concept, or rather the quantization concept of wavelength in music in his atomic instrument. Is it not very interesting? Very interesting. And as you know, now you can, I think you can predict this picture, this figure. Who is this person?
Yes,
Who is
sir.
this person?
So Niels Bohr.
But electron is behaving like wave.
Sir Louis de Broglie.
Good.
Sir, de Broglie.
De Broglie.
Sir Louis de Broglie.
Right. Thank you. So that is the concept he introduced, that 2 pi r equal to n lambda. But he basically got it from the wavelength concept, and he was just trying to fit a complete wave or 2 waves or 3 waves, not any 3.5 or 7.25, a complete integer number of waves in the radius, Bohr's radius. So that is the concept he got it from class 11, 12, right? But at that time, no one told you that how really he got the idea, right? It is not something that he got it out of blue or in the dream, right? Or God gifted. No, it was by logic, by some intuitive logic, that the concept of wavelength quantization as it happens in the world of music. So the rest of the thing, you know, the whole calculation, de Broglie 2 pi r n lambda, how it leads to Schrodinger equation, I mean the Bohr's equation, and the reverse, how Bohr satisfies de Broglie and how de Broglie satisfies Bohr. That is a typical BSc questions, right? But we are not very aware that actually what it is there. Now let me read out. When the electron moves around in an atom, its associated wave, so he is associating some wave with the electron, right? Its associated wave is stationary, that is in a standing wave pattern, like a wave moving along a violin string fixed at its ends. So a violin is compared with the atom. In this situation, only certain discrete frequencies are produced. So quantized, discrete. The fundamental and its overtones, as any good music student knows. So fortunately, de Broglie was a good music lover. So try to love music from today, who are not in love with music. Is there anyone who is not in love with music? No, I think everyone is in love with music. What music? That's a different question. Well, so this is from a cover from a very famous book, this Prims. The book is Little Prims. Little Prims. It is translated in more than 100 languages over the world. It is basically written in French and then in many languages, including Bengali and English. I have read both the Bengali version and English version. Maybe after a few months, my daughter will explain French version also, because he is learning French. So it's talking about the accommodation of the wave character of electron, or accommodate the electron as wave inside an atom, right? So you can ask the question that how, even okay, I understand that it is coming from music, but how he really could think of such a very peculiar idea, very innovative idea, how he could connect this with the music, right? It is, to me, it is because the time in which he was there, at that time already 3 quantization concepts were in the air: Planck's, Einstein and Bohr. So that's how he got the idea that quantization has to be there, and music is also there on the other hand, that wavelength is quantized. So now due char, he just connected music with, or wavelength with, the concept of electron. But it is nothing new as such, because quantization is already there. But what is new, and you know the simple formula, the formula is so simple, what was given by de Broglie. Can you give me the formula, that landmark history changing formula of de Broglie?
Lambda is equal to h by p.
Right, p equal to h by lambda, lambda equal to h by p. So have you ever seen such a simple looking formula which has won Nobel Prize? Yes, of course, E equal to NH nu, Planck, then Einstein equal to NH nu, then Bohr MBR equal to NH by 2 pi, and then de Broglie P equal to H by lambda. So that's why actually I say sometimes to my students that you try to remain simple because simple is beautiful, right? Simplicity is beautiful or beauty. So you see all this formula are actually so simple, but simple to look at. By its significance, they are very, very profound, right? So P equal to H by lambda. So P is, momentum, the associated with some particle, or H by lambda. On the other hand, lambda is something associated with wave. So this simple equation, it looks so simple, but actually is so complicated because it accommodates both the particle character and the wave character, and that's why we call de Broglie wave particle duality. So in the same equation, these two things are there, wave and particle. So now let us see what it says, that I am convinced that the wave particle duality discovered by Einstein in his theory of light is absolutely general and extends to all the physical world. It seems certain to me that the propagation of a wave is associated with the motion of a particle of any sort, photon, electron, proton, or any other, you, me, everyone. So here interesting question I like to pose here, that de Broglie is saying that actually the duality concept came from Einstein in 1905, and there he was talking about that light is okay, Maxwell, light is wave as we have explained, but now take it from me, light is behaving as particle as well. So that is the first time we got the duality, right? Isn't it? Both particle and wave. But again, this is coming after 18 years, after 1905, it is coming from 1923, and he is getting his Nobel Prize for this, again the simple duality concept. Then again you can ask the same question, yes sir, duality is so special, but already for duality one has got his Nobel Prize. Then is it so that de Broglie doesn't deserve that Nobel Prize again because of the same concept of duality? Now you tell me whether this looks like sounds like a question, valid question or not. That yes sir, you have not thought of, but yes, this is a question. At least one of you please unmute and tell me. That do you think so? That it's a question? Can you hear me? Can you hear me?
স্যার বলছি আমার একটা প্রশ্ন আছে।
আমি প্রশ্নটা তো পরে শুনছি, তুই আমার প্রশ্নটা আগে উত্তর দে, যে যেটা বললাম সেটা কি একটা ভ্যালিড প্রশ্ন? ও তুই শুনতে পাসনি, আচ্ছা তাহলে অন্য একজন কেউ বলুক, তারপর তুই প্রশ্ন নিয়ে ফিডব্যাক করবি। Anyone else? Could you hear? Let me repeat the question, that Einstein was awarded the Nobel Prize because of some concept which is basically you can call duality concept, because he was explaining that light is behaving as particle, and earlier to that light was already wave. So wave is there, particle is there, both are there, so it is dual character. Now after 18 years of Einstein, in 1923 de Broglie is again proposing something, and that is basically duality, and he is mentioning, you see, I am convinced that the wave particle duality discovered by Einstein. So my question, is it really of Einstein for which de Broglie got the Nobel Prize in 1923 work? He is also talking about duality, P equal to H by lambda. So is it a question or something, some catch is there in my question?
Yes, sir, there is a catch.
There is a catch, but could you catch that catch?
No, sir.
No, sir.
Not.
So that's why we are here, sir, with you. Okay, thank you. The answer is simple. First of all, yes, both of them are talking about duality. The second point, but they are not talking of duality of the same thing. When it is Einstein, he is talking about the dual character of light, L-I-G-H-T, light. And when de Broglie is talking about duality, he is talking about electron. To Einstein, light is basically wave but behaving as particle. But to de Broglie, electron is basically particle but behaving as wave. So now the whole cycle is complete. It's a reverse journey. It's a both-way traffic. That one side particle is there, electron, and it is behaving as wave. On the other hand, light is wave but behaving as particle. So now the next question that actually I will explain in my next delivery, that why Einstein could discover the one-way traffic, that light is both particle and wave. But why and how he failed to grasp the idea, the reverse journey, that why it's not valid for light, for electron as well, that electron is basically particle but it should behave also as wave, because particle wave duality is already there in his mind, none other than himself, but he failed. And that is a question raised by Roger Penrose in his one of his forewords of a book. And I was just excited because I used to ask the same question to my learned friends, and they told me that, okay, you are talking about philosophy, it's not science, you just forget about that question. But I insisted to ask this question in many seminars to my learned friends, that is it not a question that why Einstein failed? Because Einstein got that idea, basic idea of duality, but he applied it to light but not to electron. And on the other hand, de Broglie is a young man, he was 27 years old, and he challenged Einstein that, sir, you are correct, but you are even more correct, that you didn't understand, and that is electron 2 is behaving as a dual something, right? So that why it happened so, I will try to explain in my next lecture, but that's my own perception, that's my philosophical perception, and it's really about philosophy, not about the science, philosophy behind science, of course. So that is the formula, equal to mc connected somehow, p equal to lambda equal to h by p, that is known to you. And you know, this is something historical interesting, that when de Broglie proposed his, what happened? Something is wrong. When okay, let me explain. When de Broglie submitted his thesis, then in the committee a few people were learned people were there, but they simply didn't believe the idea that electron is behaving as a wave, and that a young man, he knows nothing about the modern physics, and basically he is drawing analogy with music. That all rubbish. They thought that, okay, it can be a good novel to be published in and sold out in College Street, like somewhere like College Street, but it should not be placed in the science rack library. So they were about to refuse the thesis of de Broglie. Okay, then one of them, fortunately, one of them, the 4 referees, did a wise thing. He just sent the copy of a thesis to the big boss, Einstein, and asked for his comment. And fortunately, Einstein went through the thesis and he told that, I believe de Broglie's hypothesis is the first feeble ray of light on this worst of our physics enigma, right? To the examining committee, he is for making a call, he made a profound comment. De Broglie has lifted the great veil, and thus it happened so that the committee passed him for the PhD. So had it been otherwise, had not Einstein not called them, probably de Broglie might have not got his PhD degree. So to Einstein, this concept is not at all ganjakhuri, but most revolutionary idea, right? So Einstein couldn't think of, but he acknowledged the idea of de Broglie. So that is the greatness of Einstein, you know. Well, but how should we know now think of the electron in the hydrogen atom as a tiny charged particle circling the nucleus, jumping from one allowed orbit to another, or as a wave adjusting its length just enough to fit exactly into one of the standing wave pattern with its electronic charge somehow distributed around the circumference. So now it's a big question to both Bohr and de Broglie, that okay, then what is an electron? Is it a particle just jumping from one orbit to the other as Bohr proposed, or is it somehow like a wave, and it is the existence, whole existence of the electron is smeared over the whole atom? That means আমরা যেমন আলপনা দিই না, গুঁড়ো গুঁড়ো করে চারিদিকে ছড়িয়ে দিই, so is it like that the electron you just make a dust as much as possible dust out of that electron and you just spread it over the atom, is it like that? So Feynman actually got a question like this from a reporter, that okay sir, you scientists, you are talking about so many ridiculous things, some people are saying that it is particle, some people are saying it is wave, so what really it is, what do you think? Then Feynman is answering that okay, it's very simple, it decides its mind that what it would be. On Monday, Tuesday and Wednesday it behaves like particle, and then Thursday, Friday and Saturday it behaves like wave. And then the reporter was very serious, he believed him. He asked then, sir, what about Sunday? Then Feynman answered that okay, on Sunday he thinks that how he would behave in the next week. So this is in a joking point that Feynman answered, but actually a very interesting question, that what it is really, and the answer is it is both. It depends on how you want to look at the problem, right? So in a brief summary, it is all about the quantization, and we got quantization from three giants, Planck initially, then Einstein, then Bohr, and they were as if three separate islands, not connected with each other theoretically or by concept. Fundamentally they were three different ideas not connected to each other, and only after de Broglie came into the picture, he explained the basic thing, that well bosses, why you are saying so and how really you are connected to each other, you don't know probably, but take it from me, you are well connected because of my hypothesis. So he is the that you know, three diamonds were there, isolated diamonds, and de Broglie was the thread which gave finally the garland. তিনটে সুন্দর দামি ফুল থেকে de Broglie একটা মালা তৈরি করে ফেললেন, the quantum mala, and that is something giving you the coherence or consistency of all the three different ideas. So a few minutes more, but all are we are talking about the ideas, theories. Any proof? Yes, we have proofs, experimental proof, and as you know, Compton effect, it is in your syllabus in BSc. It explains the photon as particle. So that means Einstein's revolutionary idea was experimentally verified by Compton in 1923. But what about the de Broglie's revolutionary idea? And that are explained by experiment, two groups, Davison and German, and Thomson and Reed. In the same year, British group and American group, at the same time they explained by experiment that yes, de Broglie, you are correct, electron too behaves as wave. And there is a very interesting something to note, that it's a book, A History of the Electron, J.J. and G.P. Thomson. So this is J.J. Thomson and this is G.P. Thomson. G.P. Thomson, right? Who is G.P. Thomson? G.P. Thomson, you see here. So that G.P. Thomson who experimented to prove that electron is behaving as wave to explain de Broglie, right? So that is G.P. Thomson. And who is J.J. Thomson? He did the experiment and exhausted everything about electron as particle. He derived the charge by mass ratio, and many other things about the electron as the particle. So this is the father who is explaining electron is particle, and this is the son who is saying and explaining and getting a Nobel Prize too for saying that electron is wave. So is it not a contradiction? A generation gap. বাপ একরকম বলছে, বেটা আরেক রকম বলছে। বাপ বলছে electron is particle, বেটা বলছে electron is wave. So to me, this is the greatest generation gap. So as father and mother, everyone would like to have his son or daughter saying the opposite if both of them are saying the profound, Nobel winning something, right? But we are not that great. That's why we call it generation gap. আমরা বলি আমাদের ছেলে মেয়েদের সব খারাপ, আর ছেলে মেয়েরা বলে মা বাবাদের সবই old backdated prejudice. They cannot match a generation gap, but I would at least appreciate this kind of generation gap when father and son is saying opposite things, but both of them are getting the Nobel Prizes for that. Well, almost at the end, then we really needed, okay, so electron at this point we can say it's behaving like a wave, but then you need some mathematical tool. If it is wave, then there must be some wave equation for explanatory purpose, for usefulness. If you have a wave, then you have to have a wave equation or wave function so that you can use it for your purpose. Mathematically, you can use your wave function. So we need an equation and a wave function as a solution to that equation. And I think you can guess what I'm going to talk about. This is Schrodinger equation. So Schrodinger actually, that is the birth of new quantum theory. That means they are getting some equation. And the first given by matrix mechanics by Heisenberg, the second wave mechanics, that is Schrodinger, and the third quantum algebra by Dirac. So actually got three such solution remedy to the problem, but we being chemist, we like this one because the Heisenberg's one was so profound and so sophisticated mathematically that physics people like this approach, but chemistry people, we like the more less sophisticated, more comfortable to chemist picture, that is Schrodinger picture or Schrodinger's approach. Okay, so that is the Schrodinger equation. So that you know, since class 11, the Schrodinger equation, and later on we will see actually this is actually a postulate. So these are the Max Born's interpretation of wave function, the breakdown of determination. After these new theories, actually the classical physics foundation was a bit shattered, like the breakdown of determinism. Everything is determined. It's not true because we have now got hoop or HAP, Heisenberg uncertainty principle. So fortunately it is broken, because otherwise astrology would have been scientific astrology. They tell about that okay, at the time of your birth, if everything is known, that the position of the stars, everything, then you can calculate the whole journey of you, that means your life, whole life. Then a man can ask that why astrology is non-science? If classical science can explain Newton equation that at one point if you can calculate the everything, time and position and moment time, etc., then at any other point of time you can exactly predict the behavior of that particle. So why not that if you understand or know the data information at the time of your birth, why can't you get everything about your life? So astrology is correct, astrology is science. But then comes quantum. Yes, classically it is correct, it may looks like correct, but after quantum, the first objection that if you know precisely everything at the time of birth, right? If you know precisely everything at the time of your birth, and quantum saying it is not possible because uncertainty is there. So you cannot precisely and accurately measure something. So that is the first, perek, coffine, astrology coffine, the first perek is that you cannot predict because of uncertainty principle. And that's why you cannot predict the future course of your life, and that's why all the gems, হাতে আংটি রত্ন ইত্যাদি এগুলো কোনো মানে নেই scientifically. Of course, if you want to wear all these things as ornaments, you are free, you can, but quantum science says no, Okay, I am almost at the end. So next time, okay, you can forget this slide. I promise you that I would talk in my next lecture some of the scientific facts and explanation, but morely it would be on philosophy behind those great thought of great scientists. So you just tell me whether you would like such a lecture to delve into the depth of their minds, or are you happy with the facts only? You just tell me, then accordingly I will go ahead.
No, sir, we like that.
You will like that. So okay, thank you very much. So next class I will take a few more things on. So for today, let me declare that this is the last slide. Thank you very much for your patience hearing, and you are welcome if you have a few questions. Actually, someone was asking a question a few minutes back. You are welcome with your questions. Thank you again.